Hello friends, hope you are having a fantastic day today. So now we are going to do a full course on stacks. They are one of the fundamental data structures, and I can guarantee you that after this course you would become a master in all questions related to stacks. In this course we are going to learn what is stacks, what are the benefits, how to implement it, when to use it, what is the time and space complexity of different operations, characteristics, and we are going to do 10 most asked, most liked and most popular LeetCode problems on stacks. So without any delay, let's get started. So stack is one of the fundamental data structures of computer science. This is a linear data structure, and typically stacks are implemented using some sort of list function. So it can be either array list or linked list. But the thing is, stack is not just typical any single array or linked list. This is a special kind of list that contains a very specific property, and that is called LeetCode property. That is called last in, first out. So how does a stack typically works is that inside the stack you always have to work with the values that you are entering is always going to end up at the bottom of the stack, and then if you have to enter the next value, it will remain at the top of the stack, and you can only access the element that was last entered inside the stack. So let's try to understand this with an example. Currently, let's say that we have this an empty stack. Now for this stack, if we try to add value number 1, so 1 is going to stay at the bottom of the stack. And now for this stack, since it only contains one value, if we have to see that what is the element inside the stack, it will return us the result as 1. But let's say that we don't do that and we try to add one more element. So if we add value number 2, it is going to come on top of value number 1. And then we add value number 3, we can add value number 5, something. Now the moment over here we decide that I want to get one element out from the stack. So the moment we try to do that, we cannot directly access this element 3 or 2 or 1. We will always have to access element number 5 first, and once we kick element number 5 out or pop element number 5 out, then only we can reach to element number 3, which means the last value that was entered inside the stack is going to remain at top of the stack, and that is the only value we can access in any given moment inside the stack. And this special property of LeetCode actually comes in very handy for some very specific operations. So before learning that, let's try to understand that what a typical stack looks like in real world. You can think of a stack of books or a stack of plates. Both of these simply shows us that how does a typical stack works in the real life, because if we have a bunch of books stack on top of each other, then we can only access the book that is currently present at the top of the stack, and then we will start going bottom one by one. So same thing applies for the stack of plates as well, and this would be the best way to understand that how does the memory is stored inside the stack, and this is implemented using some sort of list function. So inside the stack, there are mainly 3 operations that we have to worry about. First operation is called push operation. So push means that you are entering some value inside the stack. Next operation is called pop operation. Pop means that some value that is already present inside the stack, you are going to access or fetch that top element outside of the stack, and then that element will no longer be present inside the given stack. And last operation is called peak operation. So in the peak, it is very similar to pop, but you are not actually fetching the value out. You are simply seeing that what is the current value that resides at that location. So let's try to understand. Currently our stack is empty. Let me push one value. So if I try to push value number 3, then 3 is going to be populated inside the stack. Then I can also push value number 4. Then I can also push value number 7, and so on and so forth. Now at this position, I decided to do a pop operation. So let me just simply do a pop operation. The moment I do that, the 7 is actually going to be kicked out of the given stack, and it is going to be returned as part of the answer. So now the 7 is no longer present inside the given stack, and it is over here that we are able to be fetched. If I do pop operation one more time, then we would have 4 also being popped as well. And then if I try to do a push operation once again and try to add value number 5, then 5 is going to be present over here. The moment I do peek operation at this moment, then I'm only going to be seeing that there is value number 5 currently present at the top of the given stack, but I would still keep or leave this 5 untouched inside the stack. I only see that what is the value associated with the peek operation. And all of these three operation actually operates in big O of one time. So there is a special way we actually implement stack inside the list, and that allow us to fetch complete all of these three operations in big O of one time. So now let's just take a quick look at the implementation for any particular given stack. So let's start implementing the stack class. We are going to use an integer array list to implement our stack class, and now let's create a constructor to open an instance of the array list. Now one by one we are going to implement our three push, pop and peek method. So let's start with the push method. So for the push method, we are not returning anything. We are taking an item, integer item as an input, and we are simply adding it to the array list instance that we have created. Now for the pop method, first we are going to check that if the given items list is not empty, then we need to return the very last element that was entered inside the stack, or the last element that is currently present inside the item, and we need to remove that from the existing array list. So here for the pop method, we check that if the given list is not empty, then we remove the very last element that was entered inside our array list. If that is not the case, and if the given list is actually empty, then we simply return the null value. And same way, let's try to implement the peek method, where it is going to be very similar to our pop method. The only difference is that instead of removing the element, we simply need to get the value of that element. And that's it. So now we have implemented the three methods for our stack. Now let us also try to implement the isEmpty method. So for the isEmpty method, we are simply checking that if the given items array list, if that is empty or not. And that's it. This is the complete implementation of the stack class. Now let us try to implement a main method and also run some operations on the given stack class. So now we have implemented our main method where we are initializing a new stack. So first of all, we are pushing three elements onto the stack. The values are 10, 20 and 30. Next, we are going to be peeking that what is the top element inside the given stack. So this should return us the answer as 30 because that was the very last element that we entered inside the list. Then we are going to pop an element. Once again, that should also return the value 30 because that was the last element that was entered. And then once again, if we do the pop operation, it should return value number 20. And in the end, we are going to simply see the peek operation. So that should return value number 10. So let's try to run this code. We forgot to change the name. Let's try to run the code. So we can see that for the very first operation, the top element is 30. Then the popped element is 30. Then once again, we pop element number 20. And in the end, after that, when we check for the top operation, we can see a value number 10. So this is how stack is actually implemented. But lucky for us, stack is actually provided as one of the default application, and we actually don't have to implement the stack class all the time. This was just simply for your information. Now let's learn that what are some of the popular use cases that we can apply stack at. And by knowing these use cases, we would be able to quickly identify during our interview or any problem we are trying to solve to realize that whether stack would be a good choice or not. So number one thing where you can think of using a stack is for any time you have to do an undo type of functionality. So what does undo functionality means? We know that inside our computer or browser, we have the functionality where it keeps track of every single step that we have gone over across any set of websites. And then if we click the backspace button, or if we do the undo button inside the software such as Word or any other PowerPoint or something like that, it is able to trace our steps back and then put us back to the previous state. So how it does it is that it actually uses stack to store that information. Let's try to understand this with an example. Suppose we currently have an empty stack and I'm trying to open a new browser session inside the Google Chrome. So the moment I first go inside the Google Chrome, I have a new empty stack being created. Now inside the Google, first of all, I decide to go to the Facebook website, which means stack is going to mark that I visited the Facebook website right now. Through Facebook, I decide to go to the X or Twitter website. So next it is going to put the value of X on top of my stack. Then I decide to go to the Uber website. So once again, the same information is going to be recorded and so on and so forth. Now at this position of Uber, I decide to click on the back button or the undo button where I want to go back to the previous state. Simply, the browser is going to pop the element that I have entered at the very last. So this is going to be taken out. Now I'm no longer at the Uber place, and whatever value located over here, it is going to do a peek operation and bring me back to the Twitter page that I was previously browsing. So this is a great use case. Now you can understand that how this LIFO property, last in first out property, actually help us to solve a real world problem. Few other important use cases that we can think of for stack is to have it in the backtracking mechanism. Because how does a typically backtracking works is that, let's try to understand this with a small example of trees. So inside any given tree, if you have to iterate over the tree, you will have to understand that what was the previous state that you are iterating over, and have you visited all of its children or not. So let's assume that I have currently this type of scenario and I'm trying to go in the depth first search fashion. Now I know that this was supposed to be a course on stack, but I'm just explaining you some simple theorem to understand that how stack can be used with different data structures as well. So in the depth first search, we actually go in one single direction, and the moment we try to find some value, if the value is found, that is great. If that is not found, then we have to do the backtrack and do the same operation for the remaining children or remaining leaves as well. So let's try to do that. Let's say that we are trying to find this particular element and we are doing a simple depth first search. So first we are located at this position. So we are going to go to the left child, once again to the left child, and once again to the left child. We did not find the element we were looking for. But the thing is, there might be some path that we haven't explored. So we are going to do the backtracking, and through this backtracking, now we are going to see that, hey, are all the children of this particular node that I have tested? No, I haven't tested them. So I'm going to check one more. Once again, I did not find what I was looking for. Once again, I'm going to do the backtrack, and through here, so now I have tested both of his children, which means now I will need to do the backtrack operation once again. And through here, okay, there are still some children that I haven't tested. So I will go on the right, and once again, I will go on the left, and I found the value that I was looking for. And at every given moment, a stack is going to keep track of every single information that we were iterating over, so we can quickly backtrack to the previous position that we haven't iterated over. Let's try to understand this with some examples. So let's say that these values are A, B, C, D, E, and this is F and I. Okay, let's say that this is I. So initially our stack is going to be empty. Then we are at position number A. Then we move to the position number B. Then we move to the position number C. Then we move to the position number D. At D we realize we cannot go further anymore. So we will pop D out, and we will check that have we explored every single possibility at this C? No, we haven't checked. So once again we are going to go to the value number E. So we are going to add value number E over here. Once again, we haven't checked all the possibilities. We check all the possibilities at E. Once again, we come back to the C. We check all the possibilities at C. So we are going to remove C as well. Now we are at this position number B. So at B, we haven't checked F. So we will add F over here. From F, we haven't checked I. And we are going to reach to the I, and I was the item that we were looking for. So we found our answer. So we can simply say that, yeah, this element is present inside this tree, and we were able to smoothly iterate over the entire tree using backtracking because we had the stack that contained the last in first out property. So now you start to understand that how specific or how important stack is. Let's try to understand one more use case, that is that at any given moment you want to identify that whether the given sequence of, let's say, brackets or parentheses, are they valid or are they in the correct order or not. And doing this can very easily be done using stacks. How? we can simply have a logic that whenever we identify an opening parenthesis, we are simply going to add that value to the stack, and whenever we identify a closing parenthesis, we will remove that value from the stack and see that the value removed, does it contains the same type of parentheses or not. So let's try to see the example in action, and then you would be able to understand what I'm talking about. So first we encounter a square opening bracket. So we are going to mark square opening brackets, then curly opening bracket, and then a round opening bracket. Okay, so now we took care of all of these three elements. Now we are at this position and we encounter a closing bracket. Now the thing is, in order for this sequence to be valid, the closing bracket has to be exactly the same way that was for this particular bracket. So let's try to do that. So let's say that we pop this element out, and over here we identify that for this circular closing bracket, the value we popped out was also opening bracket, which means this is a good sequence, so we can move forward. So now we no longer have this value. Next we have a curly closing bracket. So for curly closing bracket, we realized that the value we popped out was also curly opening bracket. So this is also a matching pair, that is good. And in the end, we found out that the last element is also a closing bracket, that is square closing bracket, and the value we popped out was also a square closing bracket. So we found this pair, which means this pair of parentheses is valid. Now the question is, this is really important whenever you are building IDEs or compilers. So things like IntelliJ, Eclipse, or JetBrains, or bunch of other compilers, they all use this formula or the stacks to keep track of every single opening and closing bracket. Now imagine in this scenario that this last element, say for some reason, this one is a circular closing bracket. Now at this moment, we identified a circular closing bracket and we try to pop this element out, and we identified that this was actually a square opening bracket, which means this was a mismatch. So if that is the case, we can simply get rid of these things, saying that this was an invalid pair, and that is how we can use stack to complete these type of operations. And we can do all sorts of like functional logic and all sorts of important fun stuff using stack. So that's why they remain so popular in terms of technical interviews. And now we are going to go ahead with the 10 questions about stacks that we talked about. Completing these 10 questions will give you the full exposure towards stacks. These are some of the most popular, most liked, and most asked problems in terms of technical interviews. All of them are really popular LeetCode problems, and they have been asked in interviews tons of time. So without any delay, let's get started. So today we are going to solve daily temperatures LeetCode problem. That is a medium problem and also an extremely well-liked LeetCode problem. So the problem statement is quite simple. We are given an integer array called temperature that represents the daily temperature over a certain span period. Now we need to return a new answer from this given temperature array such that any particular item in that particular answers array should define that how many number of days you have to wait in order to generate a warmer temperature compared to that particular day's temperature. So let's try to understand this with an example. Suppose this is the temperatures array we are given. Now in the input you can see that bunch of different values for every single day's temperature. Now if we see, on this very first day, the temperature is 73, which means how many number of days we have to wait in order to get a warmer day. Well, a warmer day is right next, which means if we just wait one more day, we can actually get a warmer day. Same way for 74, if we just wait one more day, we also get a warmer day because next day's temperature is 75. Now at this 75, if we have to find a warmer day, then we have to find a day that contains higher temperature than 75, which means this temperature 76 is higher, which we can see that that is actually 4 days away. So over here we will have to actually wait 4 days in order to get a warmer day. Same way for this 71, we have to wait 2 days in order to get a warmer day. At position 69, we only have to wait 1 day to get a warmer day. At 72, once again we will have to wait just 1 day because next day is 76, which is warmer. At this 76, we do not find any particular warmer day subsequently, which means we cannot find a warmer day. So we are just going to mark this as 0, that no warmer day exists in front of the value 76. And last one is 73. So since this is the very last entry, we don't know what the upcoming temperatures looks like. So we are also going to return 0. And this is the answer array that we need to return that defines the days you have to wait in order to get a warmer day from any particular day. Okay, so first let's try to understand a brute force approach to solve this problem. The idea is very simple. We simply go to a day and then we keep on iterating the array until we find the next day that has higher temperature. The moment we find this one, we actually find the difference between the index positions, and whatever the difference is, we mark that in the answer. So for this first one, we can mark first as the answer. For the second one, once again, we are going to repeat the same process. We are going to iterate over every single value inside the array till we find a higher value, and which we find 2 days later. Same way we are going to keep on repeating the same operation, and eventually we would have our entire answer array to be populated. Now this is the most simplest method, but we can inherently see some issues with this approach. The number one issue is that at any given position we will actually have to traverse over maybe the entire rest of the array in order to find the optimal solution. What if let's assume that this, instead of being 50, maybe this was 80, and we don't have any particular solution in mind. We would have still iterated over the entire array, and then once again in order to find the lower temperature for this next element, we would still have to iterate over the entire given array. Maybe this was 82. So in this case, this is an inefficient approach, and if we see, time complexity for brute force approach is going to be big O of n square in the worst case scenarios. So let's try to see if we can improve upon this time and space complexity or not. The thing is, at this given location, at the very first moment, we don't know that what is the temperature that is higher than this one, because we have only iterated this one element, right? But what if we are at this element, we can at least predict that how many elements actually has lesser temperature than this, and based on that we can immediately update their temperature, and we can immediately say that for if we are at, let's say, value number 75, then at 75 we should be able to tell that 74 is only 1 day away from having its warmer day, and same way at 74 we should be able to tell that 73 is actually just one day away from having a warmer day. Same way at 72 we should be able to tell that 69 is only 1 day away. So how can we actually do that? For that we will have to find some way to actually iterate the array in one direction, note that what the current temperatures are, and based on that we will also have to check that what are the immediate temperatures that are actually smaller than this current temperature or greater than this current temperature, so that we can mark their answers. In order to do that, we will have to use an extra data structure to store the values of all the temperatures for which we have not been able to find the warmer days. Second thing is, for any particular temperature, not only we will have to find the warmer day, we will also have to find like the immediate warmer day. So for this 75 is actually greater than both 74 and 73, but we should not waste our time marking this 73 as having a warmer day as 75, because there is 74 that is more closely associated with 73, which means we have to worry about the immediate before elements. So we are traversing in one direction, but at the very quickly we will have to understand that what was the last item we were at before moving to any particular previous elements. So the best data structure in this case is going to be a data structure that contains the property of last in first out, and the answer becomes very simple, that we are actually going to use a stack to solve this problem. Now how we are going to use the stack is actually quite interesting. Let's first understand a couple of properties. Number one thing is, we are using the temperature to compare the difference between any two given values, which means we are dealing with the value of this given array. But in the answer, we need to store that how many number of days are apart between any two entities, and that we can find using the index values. Why? Because at index value 0 we have this value 73, and at index value 1 we have this value 74, which means index value 0 is only 1 day away from finding a warmer day, because index value 1 minus index value 0 becomes actually value number 1. So this is how we are going to find the answer, which means in the stack it would make more sense to store the index positions rather than storing the actual values. But using the index positions, we can very quickly look up inside the array, find the answer, and then subsequently traverse the answer. So after this long explanation, let me walk through the solution that I'm proposing. So currently we are at 0th index, the value is 73. Currently we don't have any value inside the stack, so we are going to add index 0 inside the stack. Okay, and now we are at index position number 1, the value is 74. The very first thing we are going to do is we are going to check that whether the value located at 0th position, which means the value located at temp of 0, if that is actually less than the current index positions we are at. So if that is less than the temp of 1, which is correct condition, because this one was 73 and this is 74, which means 70, this value can be popped out of the given stack, and we can actually mark the answer for this one by doing the subtraction between the current element minus the index position that we just kicked out from the stack. So this is going to be just 1, where we did a simple equation 1 minus 0. Okay, now we are going to put 74 in the stack, but we are going to put the index value. So now in the stack we have index position number 1. Now once again we are at index position number 2. So this value is 75. 75 is greater than 74, which means we can do 2 minus 1 and the answer is 1. So we can store that 74 is 1 day away from finding a warmer day. Now we popped out 1 from the stack. Now let's add entry number 2 inside the stack. Okay, now we are at this position 71. So currently 71 is actually smaller than 75, which means we don't, for 75 we have not yet found a warmer day. So we are going to add entry number 3 inside our stack as well. Next we are going to be at position number 4, which is 69. Once again 69 is actually less than the current top value we have inside the index, which means we haven't found a warmer day for this top element, and we are going to add one more element that we haven't found a warmer day for. Okay, now we are at position number 72. So 72 is actually greater than this value, the value at index number 4. So we can actually find the answer for index number 4. So let me just go. Okay, so this is for index number 1, 0 we have, 1 we have, for 2 we don't have, for 3 we don't have, but for 4 we found the value, that is 5 minus 4. So we can add 1 as the answer for index number 4. Once again, the moment we pop out index number 4, we should not be pushing index number 5 yet, because we still have to check that whether 5 is greater than index number 3, and yes, it is once again greater. So for index number 3 we are going to mark the answer as 2, and same way for index number 2 we are also going to mark the answer as for index number 2 we are still not able to find the answer, because this is 75 and this is 72. So we are going to have index number 2 still living inside the stack, and then we will have index number 5 now residing in the stack. Now we are at index number 6. So this value is 76. 76 is actually greater than 72, and so in this case we can actually mark down the answer over here as 1 for this index number 5, and we can get rid of this index number 5. Now once again this index number 2 is also smaller than index number 6, so we need to do the difference, 6 minus 2, so we find answer 4, and we are going to populate answer 4 over here. And then we have an empty stack, which means there are no more values we need to check, so we are going to add value number 6 inside the stack. And then in the end, next value is value number 7. So 7 is 73. 73 is actually smaller than the current stack value we have. So we are also going to add value number 7 inside the stack. And the moment we reach to the end, we are going to fill out all the rest of the elements by 0, that there are 0 days that we have been able to find the answers for. And this is what we can return in the answer. So you see how using a stack we actually need to traverse over just once on the given temperature array, and then we have been able to find the answer, which means this is a much better approach, and this is the optimal solution compared to our brute force solution. So let's try to see the time and space complexity. In this case, the time complexity is actually going to be big O of n, because we are simply iterating over the temperature array once. Now it could be possible that for some values we might have to go back and find the values that are smaller than that where we are doing multiple operations inside the stack, but that number is going to be limited, because we are being told that we can find out that how many values are there, and we are only iterating over the values for which we haven't find the answer. And in terms of space complexity, once again, in the worst case scenario, this is going to be big O of n, because we are using an additional space, additional stack to find the answer. So the coding solution is actually quite straightforward. First, we initialize a number n in order to mark down the length of the given array. Then we initialize a new answer array of the size n. We also initialize our stack that we are going to use. Now we simply iterate over the given temperatures array using the for loop. We first have a while loop condition that while the given stack is not empty and the temperature that we are iterating over currently, if that is greater than the temperature that is currently present inside the stack, then we simply mark the index value that is currently present at the very first element of the stack that we popped out, and then we mark the answer index by doing the subtraction of I minus the current index position that we have just been able to find by popping the element out of the stack. And then we simply push down the element inside the stack, and in the end our answer array should have all the answers, so we can simply return that. Now let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs pretty fast compared to most of the other solutions. It is also decent in terms of space complexity. And once again, the solution is available on our GitHub repository. The link is in the description, so you can check it out from there. So the LeetCode problem we are going to solve is called evaluate reverse Polish notation. And we can see that this is a LeetCode medium problem and also an extremely well-liked problem on LeetCode. The problem statement is quite straightforward, but it actually has bunch of different conditions that we need to understand. So we are given an array of strings called tokens. Now these strings represents an arithmetic expression in the reverse Polish notation. Now we need to evaluate the expression and we need to return the integer that represents the value of the expression. Now let's try to see some of the conditions that we are given. Number one, the valid operations are plus, minus, multiply and division. So these are the four operations that we can imagine to expect in our string that is coming in. Now we are being told that each operand may be an integer or another expression. So we will see this in another example. Then we are being told that the division between two integers always truncates towards 0, which means we are always considering the the floor value of any equation. And then we are being told that all the inputs are going to be valid and there are not going to be any issues. So let's try to see one example, one very simple example. So in this case, the answer is going to be that the moment we identify an operator, we will have to go back and take the previous two elements, and if these two are whatever the numbers are, we are going to be using that with this operator. So we are going to be treating this as A, we are going to be treating this as B, and since this is a plus operator, we are actually going to be doing A plus B. So we need to return 3 as the answer in this case. Let's try to take some slightly more complex examples. First we are going to, okay, so this is the number, we move ahead. Once again a number, we move ahead. We identify an operator. So now we are going to be treating these two values as A and B. So we are going to be doing A plus B. So 1 plus 2. So the answer of this portion is actually going to be 3. Our equation looks like 3 and then 3 and then plus. So once again we are going to be doing 3 plus 3. So the answer is 6. So out of this operation we need to return 6 as the answer. So this is the whole logic of what the problem is actually asking us to solve. That whenever we are given the values, we keep moving forward until we find either one of these three operators like plus, minus, multiplication or division. The moment we identify these four operators, we are going to be treating the previous two values as A and B and then apply this operator and then keep on repeating the same process until we run out of every single digits inside the given inputs, and we are being told that all the inputs are valid. Now after this extensive explanation, let's try to understand the most simplest brute force approach. So brute force approach is actually quite straightforward. Suppose we are given the values 4, 5, plus and then minus and then 7. Suppose these are the values we are given. So idea is that we are going to keep on iterating one by one. The moment we identify an operator, then once again we go back to the previous two elements and we use it with that operator, and then once again we identify, okay, so now this becomes 9 and then minus and then 7. So once again we keep on repeating the same operation using the operator. But the thing is, many times, for let's assume that if this is a very long string and we identify operator at very late, the moment we identify operator, once again we are going to be repeating the same process in order to find the values a and b. So this becomes very tiresome operation. So the idea is that we need to make it better and find some smarter ways to keep track of all the elements from the point we find the operators in the reverse order, and also have an idea on how we can keep on moving forward with the given input array and start parsing the values. So these are the two main considerations that we will have to understand. So the idea I am suggesting is that we can actually use stack to solve this problem. So suppose this is the long operation that we are given. Now the idea I am suggesting in using the stack is that at the very beginning we are actually going to be iterating the same way we are iterating. All the values we find, we are going to be pushing these values inside the stack. The moment we identify the operator, we are going to be popping the previous two elements and treating them as a and b, and then applying that operator with that value. And once again, whatever the answer we find, we are also going to be pushing those answer inside the stack, and then we are going to keep on repeating the same process until we identify the operator. And then when we reach to the end, we should have our answer ready, because we are being told that the given input is actually valid. So let's see the solution in action. So currently our stack is empty. Now we are at very first element number 2. So we are going to be pushing element number 2 inside the stack. Now we are element number 3 and once again element number 7. Okay, now we identified an operator plus. So the moment we identified the plus operator, we are actually going to be popping these two values out. So if we do that, we will have value 7 and 3 that we need to do the sum of. So 7 plus 3 is going to give us the answer 10. So currently the answer of this portion is going to be 10. So we are going to be pushing this 10 inside the stack. And now look at the stack. It actually contains the equation for this portion, because sum of these three values is 10, that is present over here, and then 2 was already here. Now we have 10 and 2. Once again we identify a multiplication sign. So we need to do 2 times 10. So we get the value as 20. So now once again we are going to be pushing the value 20, because we already popped out 2 and 10. Okay, so now we have value 20 inside our array, and now we once again identified value number 8 and then once again value number 19. So let's push that. Okay, after doing that, now we identified symbol plus. So once again for plus, we are going to be doing 8 plus 19. So the answer is going to be 27. Okay, so now we are, because we popped out 19 and 8, we push 27 down, and then we have this minus operator. So last operation we are going to be doing is 27 minus 20. So the answer is going to be 7. So 7 is what we need to return in this case to solve the problem. And this is the whole solution that I'm proposing using the stack. Look how beautiful it is. Look how at any given moment, but the moment we identified the operator, we can actually find the previous two elements back, and we can actually do the sum that needs to be done, or some division, subtraction, whatever. And this is how we can solve the reverse Polish operation very beautifully using stack. This is one of the most awesome way to use stack in the real life problem, and that's why this is such a popular problem that we have seen in tons of interviews being asked. So if we see time complexity in this case, the time complexity is actually going to be big O of n, because we are going to be iterating over every single character just once, nothing more than that. In terms of space complexity, we are using an additional stack. So depending on how apart the characters are from any operation, the size of stack can increase or decrease, but overall it is going to be big O of n. So which is good and acceptable time and space complexity in this regard. So now let's see the coding solution for this one. So the idea is quite straightforward. First of all, we are going to be initializing our stack. Then for every single token, we are first of all going to check that if the given token is operator or not. If the moment we identify that if the given token is operator, we are going to be popping two values out. So first of all value we pop out is going to be our B, and second value is going to be our A. And then we are going to be applying our operator that we have found using this method. So let's see couple of the helper methods. First helper method is the is operator helper method, where we are simply checking that if the given token is equal to any of these four values. And second one, we are applying the operator where we are simply going to go over the given input values, that is the string and then a value and b value, and we are simply returning depending on the operator to whether do the addition, subtraction, multiplication or division. And if none of this case is there, we are simply adding one extra argument, but I don't think this is going to be called because we are being told that the given input is valid. If that is not the case and we did not find that these are the operator, by the way, the moment we identified the operator, we also do the calculation, and whatever the result we found, we once again push it down the stack. If that is not the case, which means the given token is not an operator, so we simply push it down the stack, but we first of all convert the value inside the integer because we know that this is going to be the integer value. And once this loop runs, we should have been done with our reverse Polish notation, and whatever the value left inside the given stack would be the answer that we need to return. So we can simply pop the very last element. So let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs pretty fast in terms of time complexity, which is pretty awesome. Once again, the coding solution for this problem is present inside our GitHub repository, so you can find it from there. So the LeetCode problem we are going to solve is called min stack, and you can see that this is a LeetCode medium problem and also a very well-liked problem on LeetCode. The problem statement is very simple, that we need to design a stack that can support push, pop, top, and retrieving the minimum element inside the given stop, these four operations, and it needs to run in constant time or big O of one time. So we need to implement the min stack class, and these are all the methods that we need to implement. Now we know that how does a typical stack work. Stack operates in LIFO principle, last in first out. If we decide to push element number 3, then we will have an entry 3 presented inside the stack. Next we can push another entry called 1, then once again we will have entry called 1, then once again we can have push another entry called 5. So currently we have 3 elements now inside the stack. If we have to pop this element, then the element 5 would pop out. So let's quickly pop one element, so then we will get an answer number 5. Then if we do pop once again, we will have value number 1. After doing that, if we were to add two more elements or push 2 more elements, let's assume 2 and 6. So once again we will have elements 2 and 6, something like this. Then if we do top operation, at this moment it should return answer 6 because that is the top element inside the array. And then if we do get min, then it should return us the value s2 because this is the current present minimum element inside the given stack. So these are all the operations that we need to do. We need to solve all of these in big O of one time, which means we will have to do something different when we are designing our stack. So what are some of the considerations that we can do? The thing is, this push method, pop method and top method, all of these 3 methods can operate in big O of one time, no issues with that. In either case, this get min is a little bit tricky because we will need to know that what is the minimum element at any given moment. Now the very first thing that comes to our mind is that when we are designing the stack, why don't we just have an extra variable called min to keep track of the minimum value we have encountered so far. So currently this is an empty stack. Let's assume that we enter value number 5. So this has been the minimum value so far, 5. Next we add value number 6. So 5 is still the minimum value. Next we add value number 2. So once again we update this and add 2 over here. Once again we add value number 7. So now currently the minimum value is 2. But now there is one problem that you did not see. And that problem is that let's assume that we decide to pop one element out. So now currently 7 is no longer here. But once again the minimum variable is still 2 because that is the minimum variable. Let's say that if we do pop once again, so once again 2 is now no longer inside the given stack as well. So now if we do min operation, we don't know that what is the minimum value inside the array because we just overrode the value. So if we have to check for the minimum value, we will have to pop all the elements out of the stack and then find the minimum value. That is option number 1, which takes big O of n time. And if we don't do that, we basically don't have any other way. So now to overcome this issue and to keep track of the minimum value at every single variable, we can actually do things slightly differently. So the moment we are storing the values inside the given array, we are actually storing different nodes, right, for every single location. Now in this design of node, we can actually have node have multiple items, not only just its value. So let's assume that this is our given node. And so in the node, I'm suggesting to add three values. First value is the value of the node itself, that whatever the value we wants to enter, that is your integer value like 1, 2, 3, 4, whatever you wants to put. Next is that what has been the minimum value up to this point inside the existing stack, and if we keep on updating this value with every single entry inside the stack, this would be pretty easy to maintain. And last thing is the reference to the next node, because in case we will have to remove or get rid of the element, we might need to update the minimum value we have entered so far. So let's see that how would this approach is going to look like. Let's say that we want to add these values inside the stack. Okay, so first we want to add value number 3. Currently the node is empty, so because node is empty, we are adding value number 3. What has been the minimum value we have added so far? That is also going to be value number 3, and the reference to the next node is going to be null, so we are not going to be concerned with that this is the very last element inside the stack. Okay, now we need to add value number 5, so we add value number 5, but what has been the minimum value is so far? So for that, we can either check the minimum value of the next pointer using this next pointer. So we check that what has been the minimum value of the next pointer at location number 5, that is value number 3, and what is the value of this current value we are trying to enter, that is value number 5. So whichever is the smaller number, which is 3 in this case, so we will still mark 3 as the minimum value we have been able to find, and then we simply have a reference to the next node. So reference to the next node, once again I'm just marking as 3, but that is simply going to be this node. Okay, once again we want to enter value number 1. So now at 1, what has been the minimum value up until this point, that is this value number 3. So instead of using 3, because 1 is smaller, so the smallest value so far is going to be 1, and the reference to the next node is also going to be this one. Same way, now we want to add value number 7, but what has been the minimum value we have been able to find so far, that is value number 1, and then just the reference to the next node, and then in the end the value is 0. So now the value is 0. We are trying to see that what has been the minimum value up until this point, that is 1. So compared to 1, 0 is smaller. So then this is also going to be 0. And then we simply have a reference to the next node. Okay. So now this is what our stack looks like. We are simply updating the node that we are storing the values in. And now let's see each of the operation. So I just mentioned that push operation can happen in big O runtime because we are just simply pushing one node inside the stack. Let's try to do a pop operation. So pop operation can also happen in big O of one time because we are simply popping one element out. So we will get rid of this element. Okay. Now once again, let's try to do the top operation. So top operation, we can return 7 immediately because that has been the latest value we find. And then if we do the get min operation, this can also happen in big O of one time because we can simply find the minimum value we have been able to identify so far. So this is the logic on how we are going to solve this problem, basically by simply redefining the way we are storing the values and then keeping track of the minimum value at every single position. That is the whole trick. And if we see time complexity in this case, well, time complexity we already know that is going to be big O of 1. And in terms of space complexity, well, this is debatable, but I think it has to be big O of 1 because anyways we are being asked to create a stack, so we cannot create extra space for that. So first let's define the node for our given class where we are going to store three values. First one is the value of any particular position. Next is the min value, and third is the reference to the next node. And this is just a simple constructor to store the values. Okay, now coming back to our main class, we are going to have a private node head and we are going to initialize our data structure here. Next, we are going to have a main push method. So whenever we need to push any single entry, so if the value is very first, then we are simply going to provide the value as it is. Then minimum value is also going to be the same value because there are no other entries inside the stack. And then the next element would be simply null. If that is not the case, we are going to add a new node where we are going to keep the value as it is. Then for the minimum value, we are actually going to compare it with the current value. and the minimum value we have been able to find so far, and that we can simply find using the next node, and then as a part of the next node we are simply going to point to the head node, and this is going to be keep on updating with every single entry. For the pop, it's very simple. We simply take the very first element that is currently present. For the top, we simply return the very first element, and then inside for the get min method, we simply return the minimum value for the head. And this is the whole solution. Let's try to run the code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs extremely fast compared to a lot of other solutions in terms of time complexity, and very efficient in terms of space complexity. So once again, I would be posting this in our GitHub repository, so you can check it out from there. And today we are going to solve a LeetCode problem called generate parenthesis. Now, if we see some of the popular companies who have already asked this question, there are companies like Amazon, Facebook, Microsoft, Apple, Bloomberg, Uber, Lyft, Google, ByteDance, Spotify, and Nvidia. So that's why I'm paying my utmost attention. I hope you also enjoy the video. Okay, so this is a LeetCode medium problem and also very well like problem on LeetCode. Basically, we are given an input number n, and now we need to generate n pairs of parentheses. So basically, we need to write a function that generates all the possible combinations of well-formed parentheses. Now these round parentheses, I think they are called well-formed parentheses. Now we can try to understand these two examples, but I'm actually going to take it one step further, and I'm going to show you 4 different examples to understand that what this problem is asking us to do. Okay, now in this first example, we are basically given n is equal to 1 pair, which means we need to make one possible pair and all the combinations of this well-formed parentheses. So obviously the answer is going to be quite simple. We simply need to return like just one possible pair that we can make out of this one. Now suppose n is equal to 2. So now for n is equal to 2, we have the choice to take like 2 of these and 2 of these, right? We need to take 4 values. So basically the number of possibilities we can make is that we can actually make a parenthesis that looks like this, and we can also make a parenthesis that looks like this. These are the only 2 possibilities we can have, and this is what we need to return as the answer. Now things becomes a little bit interesting when we reach to n is equal to 3. So when we get to the point where n is equal to 3, the possibilities we can make is, so these are the 5 possible pairs we can make when n is equal to 3. Now notice that over here for every single piece we are using like 3 opening brackets, and we are also using 3 closing brackets, but we are just putting them in different pairs so that they generate like the well-formed parentheses. Same way, if we try to do it with n is equal to 4, the answer is going to be pretty huge. So let me just draw it over here. So these are all the possible pairs we can make when n is equal to 4, and basically we are using 4 opening brackets and 4 closing brackets and arranging them in different sizes. So this is a very interesting problem. Now let's see that what are going to be the different approaches to solve this problem. So now the first approach that comes to our mind is a brute force approach. In the brute force approach, what we can do is, suppose we are given n is equal to 2, right? If we are given n is equal to 2, there is one thing guaranteed. We need to have 4 characters inside every single block of our answer. Why 4 characters? Because we are generating 2 pairs of parentheses. So 2 pairs of parentheses is basically going to be 4 characters at least, right? So what we can do is, now we have 2 options to choose from. Either we can choose an opening parenthesis or we can choose a closing parenthesis. So what we are going to do is, basically we can take every single possible pair that we can make of size 4 using these 2 characters, and only the valid pairs we put them in the answer. So suppose we are given n is equal to 2, what are the different pairs we can make? Let me make just a few pairs. So these are just some of the few examples that we can make for 4 characters using like this opening and closing parentheses for n is equal to 2. And over here we only need to find the legitimate pair. So okay, we can find one legitimate pair and we can find another legitimate pair, and I think this is going to be the answer that we need to return. So we will put these 2 in the answer and then just return them. But if you see, this brute force approach is extremely inefficient. If we see like time complexity, the time complexity goes sometimes into like 2 to the power of 2n something multiplied by n, just to check that whether the pair is valid or not, and that is disastrous. So no one is going to accept that. So we will have to find a way to do something better. So what we are going to do is, we are going to do things smartly. How we are going to do things smartly? First, let's define our purpose. Our purpose is to generate 2 pairs of opening and 2 pairs of closing brackets, and they has to be well informed or valid. Now we need like two opening brackets, so that is a given fact. We need two closing brackets, that is also a given fact. Now there are some properties that we can use at our advantage, taking consideration the definition of being valid. Now what is the definition of being valid? So basically, if we are given n is equal to 2, there has to be two opening parentheses and two closing parentheses. So that is one definition. Second definition for being valid is that we can only put a closing parenthesis if there exists an opening parenthesis before that. Again, I'm repeating myself. We can only put a closing parenthesis if there exists a closing parenthesis before that. We cannot start our answer with a closing parenthesis because that wouldn't be valid. Third thing that we need to consider is that we can only have that many number of open parentheses that is equal to the number of n. Now you are saying that why am I repeating myself? Because this is going to be the very important property that we are going to use. So now once we know all of these things, let's try to make some smart decisions on how we can actually generate the answer for valid parentheses. Basically, we are given n is equal to 2 over here, right? Now we have option to choose like two opening parentheses and two closing parentheses. So okay, now what we are going to do is for our answer generation, always we will have to start with an opening parenthesis, right? Now we created the opening parenthesis that starts with this one. Now we are going to keep track of few values. First value we are going to keep track of is the number of opening parentheses, right? So number of opening parentheses that we have used so far is 1. And what is the maximum we can use? Maximum we can use is 2 because that is the value of n. We are also going to keep track of the number of opening parentheses. We already know that is 1, right? We are also going to keep track of number of closing parentheses, and so far we haven't used any closing parentheses, so that this value is 0. And we can only add a closing parenthesis if the number of opening parentheses is greater than the number of closing parentheses, because we already proved that over here. Now using this logic, let's see that what is the sequence we can make. Okay, so first we start with this value. When we start with this value, number of opening parentheses is 1, number of closing parentheses is 0. Now over here we have two options, and those two options are we can either add one more opening parentheses or we can add a closing parentheses. So let's see options in both of the cases. The number of opening parentheses is going to be 2, and we can have this value to be 2 because we are given n is equal to 2. And in this case the number of closing parentheses is still going to be 0 because we have only used two open parentheses over here. Now in this case the answer is going to be a little bit different because the number of opening parentheses is going to be 1 and number of closing parentheses is also going to be 1, and this is also valid. Why? Because the number of closing parentheses can be 1 because we already had one open parenthesis. So far both of the cases are legitimate. Now again at this position we also have two more choices. So over here we have the one choice to open and we have one choice to close. Now let's see both the options. If we try to go one choice to open, what will happen is number of opening bracket is going to be 3, but that is not valid. Why? Because we are given n is equal to 2 explicitly. So in this case we cannot go down this path. So if we cannot go down this path, we will actually backtrack and come back to this position. Now from this position we can only go towards the path of closing. So if we go towards the path of closing, so far the number of open brackets we had is 2 and the number of closed bracket we had is 1. So that is still valid, that is still legitimate. Now again from this position we still have two options. We can either open or we can close. If we try to open, we cannot do that because number of open is going to be 3, so we are not going to go down this path. If we go down this path, basically the number of open bracket is going to be 2, number of closed bracket is going to be 2 as well. And this is the exact condition we need because we are given n is equal to 2, so which means that there has to be two open brackets and two closed brackets. So we can put two conditions, whether we can put like the combination of open plus close is going to be 4, that is going to be the double of what is n, or we can have like O is equal to 2 and C is equal to 2, both of them equal to 2. So this is also good. So now we have reached this condition, which means that whatever the path we actually make can make ourselves into the answer. So what is the path we took? So first we started with taking the opening bracket, then again opening bracket, then again closing bracket, and then again closing bracket. So let's put this value in the answer, right? So we are going to create a new variable answer over here, and over here let's put one entry. that okay, two open, two close, that is good. Now let's start following the other path. I'm going to clean this up a bit so it does not become any more distraction. So now in this case, okay, currently we have one open bracket, one close bracket. Now again we have two possibilities. So first possibility is we can open one more bracket or we can close one more bracket. Now let's analyze both the possibilities. If we try to open one more bracket, basically the number of open brackets we are going to have is 2. Let me clean this up a bit more. And over here number of close bracket we had so far is still 1. So okay, this is valid, we can put this one. Now if we try to put one more close bracket, the number of open bracket we have so far is only going to be 1, but number of close bracket is going to be 2, which is a big no. Why? Because we cannot have more close bracket than the number of brackets we have opened, because that would defy the possibility of having a legitimate scenario. So we cannot go down this path, so we won't. And now again we have two choices at this position. We can open one or we can close one. If we open one, then the number of open is going to be 3. That is not valid, that is not good. So we are not going to do anything with this one, and we will not go down this path. If we go down this path, then over here number of open brackets we have so far is 2, and number of close bracket we have so far is also 2, which is also the legitimate scenario. So which means that this path is also going to be a path that we can add to our answer. And let's see. Okay, so currently we have, okay, we have one open bracket, one close bracket. We have also have one open bracket and one close bracket, and that's it. Now initially, remember, we only started with this one opening bracket, and then we had two possibilities, and we actually exhausted both the possibilities, so we cannot go down further anymore. Now because we cannot go down further anymore, we can conclude that whatever the values we find so far, this is the complete answer, and we can return this as the answer. And basically this is the whole crux of the finding the optimal solution. Now you must be asking that hey, what we actually did was we did something very important. First we identify, okay, the one value, then we had the final case. So final case was that whenever the number of opening is equal to n and number of closing brackets is also equal to n, this is our final case. And then at every single position we had two options to either choose an opening bracket and closing bracket, and keep on repeating the same process until we reach to the end, and we had some parameters in mind. So if you see, we are actually using dynamic programming at its finest, because at any single previously computed value, that is being used to calculate that which path we need to take and whether we can take that path or not. So we are basically using dynamic programming plus backtracking to solve this problem, and this is going to be like an amazing way to explain this problem. Logically think that in the brute force, what a disastrous result we were having, and we actually brought it down to such like beautiful answer, and then we are just presenting it. So this is the whole power of using any like computer language. So before we start implementing the generate parentheses method, first we are going to create our backtrack method. That is going to be our helper method that we are going to use recursively. Now for the backtrack method, it is not going to return anything, but it is going to add all the values towards the answer. And inside the method, we are actually going to create a list of lists that is going to store the answer. We are also going to have a string builder to keep track of the current values we have, and the number of opening and number of closing brackets, and also the maximum number of values we can generate. Okay, so now first let's create the acceptable scenario. So if basically the current length is actually going to be maximum times 2, which means that we have reached to our answer and we can add it to our answer. So this is the legitimate scenario. Now let's see, say for an example, we find out that we have not reached the answer. Then what could be the possibility? Well, first possibility could be the number of open brackets that could be less than the number of maximum brackets that is allowed. If that is the case, basically for the current string builder, we can actually append an opening bracket. So let's do that. And after adding the opening bracket, basically we will have to call the backtrack method again with a reduced value of one open bracket. So let's do that. So in the backtrack method, we are going to call the answer, and we are also going to call the current string builder list we have. But for the open, we are actually going to add one value, and for the number of close brackets, we are going to keep it as it is. The max is also not going to be changed, and that is awesome. Now there is also one more important thing we will have to do every single time we make a backtrack call, and that is to delete one character that is located at the current length -1 because it is going to add an extra character. So let's do that. Okay, now same way, say for an example, if the number of closed brackets and they are less than the number of open brackets, if that is the case, basically we can also add one closed bracket to our self as well. So let's do that, and we are also going to call the backtrack method, and everything else is going to remain the same. And basically this whole logic sums up our backtrack method. Now all we need to do is from our main method, we simply need to create a list of list called answer. So let's do that. And then we are going to call our backtrack method. Now inside the backtrack method, we are going to provide the value of answer. We are also going to provide a new instance of a string builder. Going to provide the number of opening brackets that we have used so far is 0, number of closing brackets is also 0, and the maximum number of opening and closing bracket we can have is going to be the value of n. And after getting the answer from the backtrack method, we can simply return the answer to be return the answer that we got, and basically that's it. Yeah, let's try to run the code. Okay, seems like our solution is working as expected. Let's try to submit the code. If we submit the code, our solution beats a lot of other solutions. It is really good in terms of time complexity, and it is also really efficient in terms of space complexity as well. Hello friends, hope you are having a fantastic day today. So once again, we are going to do an awesome LeetCode problem. And trust me, this is an awesome LeetCode problem. So without any delay, let's get started. So now we are going to solve the LeetCode problem called car fleet. Now personally, this is one of my favorite problems, and we can see that this one is a LeetCode medium problem and also decently well-liked problem. The thing is, this is a very long description for this problem because it covers a lot of edge cases and a lot of conditions that you have to understand. If you want, be my guest and read the whole description. If not, let me just point out few important topics and then we will try to understand what the problem is asking us to do through an example that would make things much more simpler. So first thing is, we are being told that there are n cars going in the same destination along one lane road. So it's a single lane road, and we are told that the cars are not going to be overtaking each other. This is not Fast and Furious, this is LeetCode. Okay. Then we are also given a target miles that we need to reach. That is the final destination for our cars. Now we are given two integer arrays. First one is position and second one is called speed. So position defines that what is the starting position for any particular given car compared to that target distance. Okay, and the speed is at what speed that particular car is running on. So we are given both the values inside the car. Now we are being told that cars are not going to overtake each other, but if they are close enough, we can consider them arriving at the destination at the same time. And any car arriving at the destination or set of cars arriving at the destination would be considered as car fleet. And now we need to consider that how many number of different car fleets actually arrive to the destination. So I know that this was quite complicated and very extensive description. Let's try to make it simpler using some example. So over here, we are given a target value of 12 that we need to reach, and we are given the positions, and we are also given the speeds of subsequent cars. So here I have actually plotted a graph or a number sequence where this 12 is the target that every single car is trying to reach. Now this C1, C2, these represents different cars, and we can see that based on their positions inside the subsequent array, I have already plotted them on this given line. So this defines their starting position, and subsequently this portion defines that what is the speed that is given to every single car. Okay, and we are being told that the distance we are trying to cover is 12 miles, and the speeds are given in per hour basis. So which means this car C2 actually travels 4 miles in 1 hour. Okay, so now we need to understand that how we define car fleets. So let's try to understand it one by one. So we will try to go over that how every single car is actually going to reach to the final destination. And we know for sure that no car is going to overtake one other. So if one car comes closer to the other car, we would consider both of them reaching to the destination at the same time, and they would be part of one single fleet. So first, let's see. So currently this car C1 is located at position number 10 and its given speed is 2 miles per hour. We know that this C1 has to be the first car to reach to the destination because it is the closest car to the destination. So in the first hour, this car is actually going to reach to the destination and it's going to take 1 hour. But during this 1 hour period, because how do we come up with this 1 hour? Because we calculated the distance from the current position to the final destination we are trying to reach, which is 2 miles, and its speed is also 2 miles. So we can easily calculate the time that it takes to reach to the destination. Now for this C2, also subsequently, this C2 would also reach to the destination in just 1 hour. So based on this, we can conclude that both of this C1 and C2 are actually going to reach to the destination around the same time, around at 1 hour mark, which means C1 would be here and C2 would be right very close to it. So these two cars are going to reach to the destination in around the same time, which means this is going to be one of the fleet that is going to arrive into the destination. So now we already took care of one fleet. So let's just get rid of these. Okay. And also let's try to understand that we have already spent 1 hour. So during this 1 hour, what would be the position of all of these cars? So during 1 hour, the C4 would have traveled 1 kilometer. So C4 would be here. Same way, the C5 would have also completed 3 kilometers because its speed is 3. So after this 1 hour, this C5's position should have been at position number 6. But at position number 6, we can clearly see that C4 is already present, which means after 1 hour, the position is going to look something like this, where C4 and C5 are going to be right close to each other. Now remember that the speed of the C4 is 1 and speed of the C5 is 3. But because C4 is ahead compared to C5, even though it has higher speed, it is not going to overtake it, and it is only going to reach to the destination when the C4 arrives. But essentially, both of these cars are also going to reach to the destination in around the same time. And how much time will it take? Well, currently this one is at position number 6. So it is going to take 6 more hours and we already spent 1 hour, which means this C4 is going to take 7 hours to reach to the destination. And because C5 is behind that and it is able to catch up to the C4, it is also going to complete and reach to the destination in 7 hours. So after 7 hours, the second fleet that would have reached to the destination would be the cars that we just saw, that is the car C4 and also C5. So they both will also reach to the destination in around the same time. So this would be our second fleet that is going to reach to the destination. And now we already spent 7 hours, which means after 7 hours, this C3 would have been around here because its speed is just 1 miles per hour. So it would have covered the distance of 7 miles, and then still it would have 5 more miles to go, which means it would still take like around 12 hours to reach to the destination. And in the end, the C3 car would be the very final car that would reach to the destination, and still this would also be considered a fleet in its own. So over here we can see that actually we are getting 1, 2 and 3 fleets reaching to the destination. So for this given input, we need to return 3 as the answer. And this is the whole problem statement. Now I know understanding this problem statement took us a lot of time because there were a lot of moving parts and moving cars that we had to understand. But honestly, this is an awesome LeetCode problem because if any interviewer dares to give you this problem, this is not very difficult to solve, but it's very peculiar for interviewer to explain. Also, you will have to navigate through a lot of different edge cases and then think about coming up with the optimal solution. So now I'm not even going to be bothered to show you the brute force approach because that would be an insult to this beautiful problem. So let's talk about the actual complete optimal solution that we can use in order to solve this problem. And in order to generate the optimal solution, we need to make some assumptions and we need to do some calculations. So what are some of the calculations we need to do? Number one thing that is most important is that for any particular car, we will have to understand that how much time it takes to reach to the end. That is number one thing. And second thing is, cars can only reach to the target based on the current sequence locations they are present in. So even though if we see the car numbers over here, this C1 and C2 are located at the correct space, but this C3 is actually going to, even though this is the third car, this has to be the last car to reach to the end. So number one thing we are going to do is we will try to find that how much time does it take for any single car to reach to the end. We will try to store this information with the cars. So we actually have a couple of ways to store this. We can either store it using a hash map. That would only make things more complicated because we don't need like a constant time access to that data. And same thing can be achieved using a two-dimensional array as well. So we will try to use it, store it using two-dimensional array. Okay. So in the two-dimensional array, we are going to store the information for a subsequent car and how much time does it take to reach to the end. That is number one thing. Number two thing we are going to do is that we will actually sort these cars based on their positions. So number one car in that is going to reach to the destination is going to be the car that is closest to the destination position. So based on the position size, we are also going to sort them. And once we have that, we would be able to identify the answer quite easily. So now first let's try to understand that how do we actually calculate how much time does it take for any single car to reach to the destination. And that is a very simple calculation. All we need to do is we need to calculate the distance between the current position and the destination position, and whatever this distance is, we need to divide the speed by that distance, and that would give us the time on that particular car would take to reach to the final destination. Okay, so now the idea is quite simple. So let's just do that. So for C1, currently we can see that this is located at position number 10 and it needs to reach to the position number 12, which means the distance is 2. And the speed for C1 is also 2 miles per hour, which means it is going to take 1 hour for C to reach to the destination. Same way for C2, it is also going to take 1 hour to reach to the destination. Same way for this C4, it is actually going to take 7 hours to reach to the destination because the difference between 5 and 12 is 7 and the speed of C4 is 1 miles per hour. Same way for the C5, the distance is also going to be 9 miles, and then the speed is 3. So it is only going to take 3 hours to reach to the destination. And last one is the C3 car. So for C3, it's actually going to take 12 hours to reach to the destination. Now we have our this list ready. Now let's try to sort this given list based on the position of the cars, which means once again C1 is at the correct position and C2 is also at the correct position. Both times are 1 hour and 1 hour. Then we have the car C4 and C5. So for the car C4, it is going to reach into the 7-hour mark, and car C5 should reach in 3-hour marks if there were no cars ahead of it. And the last one is the C0 car, or I think C3 car. So C3 car is going to take 12 hours to reach to the destination. Okay, so let's quickly do a recap what we did. We found out how much time does it take to reach to the destination. Then we sorted all of these cars based on the position where they are compared to the target location. So the higher the position, the first it is going to be inside our L list, and in order to store this information, we are going to be using a 2D array. Now, after having this information, it becomes very easy for us to solve this problem, because all we need to do is we simply have to check, because we know for sure that this has to be the first car to reach to the destination. At any given moment, we realize that the speed of this is actually lesser or equal to the speed of its subsequent car. Then we can conclude that both of these cars would reach to at the same time. Let me rephrase. I use the word speed, but the correct word should have been time. So if the time it takes for the C1 car to reach to the destination is 1 hour, And we see that for C2, the time it takes is also 1 hour, which means C1 and C2 both are going to reach to the destination around the same time, just in a scenario where C2 is just behind C1. So we can conclude that these two has to be one single fleet. So this becomes our one of the fleets. Now in the second scenario, we have the time it takes for C4 to reach to the destination as 7 hours, and the time it takes for C5 to reach at the destination at 3 hours, which means C5 actually is much faster than C4. So eventually C5 would be close enough or just behind C4 before C4 actually reached to the destination. Let's try to once again understand using this plot, because after the very first hour, actually C5 and C4 would both be at the same place. And how do we find out? Because we can see that the time it takes for both of them to reach to the destination. So these two also has to be part of a simple fleet. Now say this last for the C3, instead of this being 12, maybe this also took 3 hours to reach to the destination. Then C3 would have also been part of this fleet, because C3 would reach to the destination in 3 hours, C5 would reach in 3 hours, and C4 is going to block both of them and cause both of these cars to reach at 7-hour mark, because C4 is ahead compared to C5 and C3. So this would have been part of this fleet as well. But in this scenario, because the time C3 takes to reach to the destination is actually greater than the previous fleet, the largest value in the previous fleet, then we can conclude that this C3 is not going to be able to catch up to the C4 and C5 fleet. So this is going to be our second fleet. And in the end, the C3 is going to be our third fleet. So that's all you need to do to solve this problem. Once we do have the sorted version of subsequent cars with the time it takes to reach to the destination, we can actually very easily compute, because for every single fleet, all we need to check is that what is the longest time it takes for those fleet to reach to the destination. So in this case, for the C4 and C5, it's gonna take 7 hours to reach to the destination. So if this number would have been anything less than 7, then it would have been part of this C4 fleet. But because it's not less than 7, so this has to be a fleet on its own. And that's it. That's what we need to do. And this is the whole solution. So now you see how beautiful this problem is and how awesome the solution is. Like, that's why this is really one of my favorite questions, because it's a combination of math and data structures, and then how do you make things more efficiently, and how can you think about different scenarios and different mathematical equations and stuff like that. Okay, so now let's try to understand the time complexity. It is going to be big O of n, because we are going to be simply iterating over the given input array bunch of times, but still it is going to be big O of n. But you forgot one critical thing, that is we will also have to do the sorting operation, and that is actually going to cause our time complexity to be big O of n log n. And if we see space complexity, well, for the space complexity is actually going to be big O of n square, because we are using a 2D array to store the information of the cars to its subsequent time it takes to reach to the destination. Overall, this is also a very good time and space complexity. Now let me know in the comments if you also want to see a solution using a monotonic stack, because this is pretty popular problem for that. So if you want, I can also show a solution with that. But I think this is a good enough solution for your interview. Your interviewer is going to be more than happy. And now let's just quickly see the coding for this one. So the coding solution is quite simple. First of all, we create an integer n to store the length of the given input array. And then we initialize our 2D array that we talked about, where we are going to store the information about cars and its subsequent time it takes to reach to the end. Then we are simply going to iterate over the given input array, and we are going to populate our cars 2D array that we just created, where we are going to mark the positions of the car, and also we are going to calculate that how much time does any single car takes to reach to the destination. Then we are going to do the most important operation, where we are going to sort the given cars based on the current positions of the given cars. Once we have that, now it is very convenient to solve this problem. We are going to initialize a counter 0, that this is going to calculate the fleet on what time it is going to arrive. And then we are going to have another variable where it is going to keep track that what was the previous time for the car to reach to the end. Then we are simply going to iterate over the given input 2D array cars, and we are going to check that if the value of any particular given car is actually greater than the previous time, which means that is a new fleet being created. So we are simply going to create a new fleet or add the value to the counter. And also we are also going to mark the previous time of the last car that just came in. And that's it. In the end, we can simply return this counter that we have created that was keeping track of every single fleet. And now let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs decently efficiently in terms of time complexity, extremely efficiently in terms of space complexity. And once again, the code is present inside our GitHub repository, so you can go and check it out from there. Thank you. Hello friends, hope you are having a fantastic day today. So now we are going to solve Facebook's most asked question. This question has literally been asked 142 times at Facebook. So this is a very popular LeetCode interview question, and without any delay, let's get started. Okay, so the LeetCode problem we are solving today is called minimum remove to make valid parentheses book, and we can see that this is a LeetCode medium problem and also a very well-liked problem. Now the problem statement is quite simple, that we are given a string that contains bunch of different opening and closing parentheses and lowercase English characters. Now at any given moment, if we identify that the parentheses are in correct sequence, like the same number of parentheses that are opened are also closed, then we call them valid. But if we identified some invalid parentheses, then we simply have to remove them. So let's try to understand this with an example. It would make much more sense. And we can see that bunch of the parentheses are actually at the wrong position. First one we can see over here, where we have a closing parentheses, but we don't have any opening parentheses somewhere here before, which means this is an invalid parentheses. Same way, this is also an invalid closing parentheses, because though this pair of parentheses are valid, this is not valid. And same way, we have an additional opening parentheses. So in this case, we have three parentheses that are invalid. So if we simply get rid of these three parentheses that we just identify, then we would have our query that will look like this. And now we can see that this entire sequence is actually valid, where we have two pairs of opening and closing parentheses, so they are valid. And also we have a bunch of different smaller English language characters, and they are also valid. So we simply have to identify that which are the index positions that we need to remove in order to make a valid parentheses pair or a valid query. Okay, so let's simply see the brute force approach very quickly. Brute force approach is very simple. For any query that we are given, all we need to do is that we simply go over every single character, and the moment we identified either an opening or closing parentheses, so in this case we identify a closing parentheses, so once again we would go back and try to find an opening parentheses. If we cannot find it, we identified that this one is invalid, and then we move forward. Same way, the moment we identify an opening parentheses, once again we would move forward to try to find a closing parentheses that is going to match up with that. If we find it, that's great. If we don't find it, then in that case we would deem that parentheses as invalid. And if we keep on moving forward in that direction, we would eventually find the answer. But the thing is, there is a lot of back and forth we are doing, and essentially for every single character, in the worst case, we might have to do like big O of n square work in order to solve this problem, which is lot of work needs to be done just to solve this problem. And this is actually a very simple problem to solve. So now let's quickly see the optimal solution for this one. So now let's try to see that what would be the optimal solution to solve this problem. And for that, we will have to understand just couple of things, that what are the exact checks we are making. Number one thing we are checking is that at any given moment we identify that any particular opening parentheses exist. This can only be valid if further down the road we identify that there exists some closing parentheses. Okay, and same way, if we identify some closing parentheses, this can only be valid if there exists a subsequent opening parentheses presented in counterpart towards this one. If there does not exist any, which means this is one of the invalid ones. So using these two conditions, what we need to do is for every single opening parentheses, we need to keep it stored somewhere that there might be a closing parentheses somewhere down the line. And the moment we identified some closing parentheses, we will have to check that whether there exists an opening parenthesis immediately before that is going to match with it. So a very good data structure in this case would be stack to solve this problem. Why? Because stack has the property of last in first out that we are going to use at its maximum to solve this problem. And let's quickly understand that what I mean. Now the thing is, through stack we would be able to tell that which parentheses is invalid. But the thing is, we would still need to recreate this entire string in order to solve this problem. So what we can do is, the moment through stack we identify that any particular indices is invalid, whether opening or closing parentheses, we can just simply create maybe like a hash set or some other data structure where we are simply going to keep track of all the variables or all the index positions that are invalid. This will help us to rebuild the entire string after we find out all the invalid parentheses. Okay, and the logic we are going to apply is that for a stack, if the moment we identify that there exists an opening parentheses, we are going to push the opening parentheses down the stack. The moment we identify a closing parentheses, we are going to check inside the stack that whether there exists an opening parentheses to counter this closing parenthesis. If it does, we are simply going to pop that parentheses out, so marking that this entire pair is going to be considered valid. Now for some peculiar case we identify that there exists a closing parenthesis but there is no opening parenthesis, then this needs to go to the set because this is an invalid entry. And using this logic we would be able to solve this problem quite easily. So let's quickly see the solution that I'm proposing. Okay, and also let me quickly mark all the index positions and also initialize a hash set where we are going to store all the indices. Okay, so very first element is a lowercase English letter element, so we will just move forward. Now we identified a closing parentheses. So now the moment we identify a closing parentheses, we will need to check inside our stack that does there exist an opening parentheses. Currently the stack is empty. Because the stack is empty, this is an invalid position. So we are going to mark the index position inside our set as 1. Next, we will move on towards the next element. This one is also a lowercase English character, so we move forward. This is an opening parentheses. So opening parentheses has to go into the stack. So we are going to mark its index location inside the stack. So we identified value number 3 over here. Okay, next is also a random character. Now this one is also a closing parentheses. So closing parentheses, we check that whether in the stack do we have any entry, and yes we do. So we will actually pop this element out. So we pop this element out. Currently stack is empty. Now because stack is empty, we also identified that there exists an opening parentheses. So a closing parentheses, and we once again needs to check into the stack, but stack is empty, which means this is also an invalid character. So we are going to mark 5 over here. We get once again we can ignore this one. Now this one is an opening parentheses, so we enter over here. Once again opening parentheses, so once again we enter into the stack. We can ignore this one. Now this 10 is also a closing parentheses. So for the closing parentheses we can pop one value out. So we pop 8 out from our stack. But the thing is, in our stack we still have value number 7 left, which means that this value number 7 is also an invalid stack because we just run out of all the characters inside the string. So we have an extra opening parentheses as well that we need to remove. So we can mark this value. And now if we remove this character 1, 5 and 7 from our existing string, we would get our string that looks like this, where the values are going to be valid, and this is what we need to return in the answer. So basically We can very easily solve this problem using the stack. If we see time and space complexity, time complexity is going to be big O of n, where n is the number of characters that are present inside the stack, and space complexity is simply going to be big O of n as well, because we are using an extra stack and also an extra hash set to store a bunch of different values. Okay, so now let's quickly see the coding solution for this one. So coding solution for this one is quite straightforward. First, we initialize our hash set and our stack. Then we simply iterate over the given string. And for every single character, we first check that if the given character is an opening parenthesis, we push it down the stack. If it is a closing parenthesis, and if the stack is empty, which means we identified an unexpected closing parenthesis, so we simply add that character to our remove indices hash set that we have created, add its index position. And if that is not the case, we simply pop the element out of the stack, because stack already has an opening parenthesis. This is what it means. Now in the end, after this particular loop has ended, we would have taken care of all the unexpected closing parentheses that were present, but we still have to take care of the opening parentheses, and they would still be present as unmatched opening parentheses inside the stack. So any single element that is present inside the stack, we simply take them out and work on and add them to our hash set as well. In the end, we simply need to build a string in order to generate the answer. So for that, we remove every single character that are present inside our hash set, and then just create and append the string that was already given to us in the input, and then we simply return that as the answer. So this is the whole solution. Let's try to run this code. And our code works as expected, so no issues with that. Let's submit this code. And our solution is pretty fast compared to a lot of other solutions. Once again, the coding solution is present inside the description of the GitHub link that I have provided below this video, so you can go and check it out from there. Thank you. This is a LeetCode easy problem, and also one of the most liked problems on LeetCode, and that is because this problem actually solves one of the very real life application where a compiler has to check that whether the code has valid parentheses or not. And so that's why a lot of companies like to ask this problem as an interview question. If we understand the problem, basically we are given a string S that contains just these three types of parentheses: opening parentheses and closing parentheses, and we need to determine that if the given input is actually a valid input or not. We are also given the definition that what counts as a valid input, that if the opening brackets are closed by the same type of closing brackets, and also we are told that the opening brackets must be closed in the correct order. So let's try to understand this with some examples over here. I have drawn a bunch of different potential examples, and we will see that if they are valid or not. So first of all, if we see this example, we know that okay, we have two opening brackets and we have two closing brackets. We can consider this as a valid string, so I'm just noting it as V. Now again, in this case, we have two different types of opening brackets and we have two different types of closing brackets, so this is also a valid string. Now in this case, this is an opening bracket, this is an opening bracket, we have corresponding closing brackets. Again we have opening and closing brackets, and again we have opening and closing brackets. So everything is in order, and the same kind of brackets are opened and correct in proper shape and size, so we can consider this also as a valid format. Now if we come to this example, this is an opening bracket, this is also an opening bracket, but we only have a closing bracket for this original opening bracket, so we can consider this as invalid option. So we get an idea why it is invalid. In this case, we have three opening brackets and only one closing bracket, so again this is an invalid string. And in this case, actually if we see the number of opening brackets and number of closing brackets, they are actually same. So we have one opening bracket and one closing bracket, again one opening bracket and one type of closing bracket, but this is still invalid. Why it is invalid? Because this bracket, this curly bracket, is actually opened before this particular round bracket, so that's why it has to be closed before this round bracket closes. And in this case, this round bracket actually closes first before this curly bracket is being closed. So this is very important property that we will have to keep track of, and that is why we are told that we need to keep track of the order in which they are opened and closed, and then only we can determine that whether they are valid or not. So this is also an invalid formula. So let's see that what would be the potential solution. So let's start from the very simple example and see that what would be the intuition behind building a solution. Suppose we are given an example that looks like this, where we are given all of the brackets that are of the same kind, and we are given some opening brackets and some closing brackets. Well, we can clearly see that this is a valid approach, and how we can determine is that we can actually create a counter. And what this counter does is that at any given moment we identify an opening bracket, we are actually going to increase the value in this counter, and at any given moment if we encounter a closing bracket, we are actually going to decrease the value in this counter. And at the end we have to check that whether the value inside this counter, if that is equal to 0, which means we can determine that the same number of opening bracket and closing brackets are present, and then we can say that the string is actually valid. If that is not the case, we can say it is invalid. So if we see that in action, first of all we have 3 opening brackets, so we will increment the value of this counter 3 times, and if we do that we will get the counter value to be at 3. Again, now we identify a closing bracket, so now this value from 3 becomes 2. Again we identify 2 more closing brackets, so again it gets decreased 2 more times, and then we get the final counter value to be 0. And because we get this value as 0, we can say that okay, this string is actually valid string, and the same number of opening and closing brackets are happening. So this is one way to identify a solution, but in this case the complexity is actually very simple. Why? Because we are only using one kind of opening and closing brackets. In our original problem we are actually told that there are 3 different kinds of opening and closing brackets, and we will have to keep track of them. Also we need to keep track that in what order they were opened and closed, and that order also has to be maintained. So it is not just as simple as keeping track of counter, that we create 3 different counters for all single type one of them, and then we see that at the end whether this value is 0 or not. We also have to keep track of that what is the order they were opened in and they were closed in. For the optimal solution, we know we need to take care of 2 things. First thing is we need to check that whether the opening and closing number of brackets are same for each 3 different types of parentheses or not. Second thing we have to take care is that what is the order in which they are opened and closed. So first let's tackle the first problem. We know that for every single opening bracket there has to be a closing bracket, and they are always in pair. So now to quickly look them up, we are actually going to use a hash map. Now inside our hash map we are actually going to have all of these closing brackets as the keys and their opening brackets as corresponding values. So we are going to have 3 entries. Now we have to take care of their order and number of occurrences. So the idea is we are actually going to use another data structure called stack, and the stack is actually going to be very helpful to us. So let's try to understand this with an example, that how we are going to use a stack over here. Suppose we are given an input that looks like this. Okay, so I'm going to show you 2 examples on how we are going to solve this problem. So first let's take this example, and the idea is that at any given moment we identify an open bracket, we are going to add that value inside our stack, and at any moment we are going to encounter a closing bracket, we are going to pop a value from the stack, and then we are going to see that whatever the value we popped out, if that is the same value that is for any given hash map value we have inside the string for that particular closing bracket. So let's see that in the action. First of all, we identify these 3 opening brackets, so we are going to add all of the entries inside our stack. So first we will add a curly bracket, then we will add these 2 brackets. Once we are done with this one, now we have a closing bracket our hand. The moment we identify a closing bracket, remember we will have to pop the value out of our stack. So we are going to pop the value out of the stack, and the value we have popped out is actually this one. Now for this closing bracket, we are going to see that what is the value of that bracket inside our hash map, and the value of that bracket is also like this, and we are going to compare these 2 elements, that whatever we took out from the stack and whatever we got from this hash map, and both are same. So because both are same, we can say that okay, we are good so far. And now so far we have actually taken care of these 4 elements, and now we are on this element. Again, this is also a closing bracket, so because this is also a closing bracket, we will have to pop a value out, and we are going, if we pop a value out, we will get a value that looks like this, where we are arrived from our stack. And now we are going to check that for this particular bracket that we were iterating over, what is the corresponding value inside the hash map. So the key is this one, and the corresponding value is this one. So the value we found from our hash map is also this one, and they both are same. So because they both are same, we can say that okay, we are good up until this point. Now we are iterating over this curly bracket, so we again pop, and also I have forgot to delete this value. Now again we pop out a value from our stack, so now we don't have this value over here, and we have a bracket that looks like this. Again, for this closing bracket, the value inside our hash map is also an opening curly bracket, and both are same, so we are good up until this point. Now we are only up to last two characters, so this is also an opening bracket. The moment we identify opening bracket, we will add an entry to our stack, and now this is a closing bracket, so again we will pop this entry out. After popping this entry out, so this is the value we popped out from the stack, and then we will compare from our hash map. So the value is this one, and both are same. So we are at the end of our string, and because we are at the end of our string, we are going to check that whether inside the stack we have any entry or not. We don't have any entry, so we can return true in this case, and we can say that the given string is actually valid, and this would be the answer. Now let's take one more example where the string is not valid and see that what we are going to encounter in this case. Suppose we are given a string that looks like this. So in this case, we have two opening brackets and one closing bracket. So first of all, we identify that this is the opening bracket. We are going to add an entry over here. Again, we encounter an opening bracket. We are going to add an entry over here. Now we encounter a closing bracket. The moment we encounter a closing bracket, we are actually going to pop out the value from our stack, and the value we popped out is actually a curly opening bracket. Now for this closing bracket, we actually have a corresponding value inside our hash map that looks like this one. Now these two are actually not same. So the moment we identify that these two are not same, we can immediately return that this string is actually invalid and the parentheses are not in correct order. So we are done with this one. Time complexity is actually going to be big O of n, where the n is the number of entries present inside the string, and even in terms of space complexity, because we are using a stack and hash map, but we don't care about hash map because it has finite number of entries. But for the stack, the values will be dependent on big O of n as well, on the number of entries present inside the string. Now let's move on to coding. So first of all, we are going to initialize our hash map, and inside the hash map we are going to store the values for three different brackets that we are given. Okay, we are done with this one. Now we are going to initialize our stack, and we are going to name it as stack as well. And now we are going to run a for loop across the given string. So first of all, we are going to initialize a character C, and that is to keep track of whatever the character we are looking over inside the given string. Now we are going to check that if the current bracket is opening bracket or closing bracket, which means that if the key value is present inside this mapping bracket, then we can define that it is a closing bracket. If not, then we can define it as an opening bracket. So if the value is not present inside this mapped bracket key, which means that we will have to push the current value inside the stack. If not, which means that the value is actually a closing bracket, and then first of all we are going to pop the value out of our stack, and then we are going to compare it with whatever the value pair inside the map bracket we have. And if the stack is empty, we can return false immediately. So in the else condition, we check that if the stack is empty, we can return false immediately. If not, we are going to pop out a value from the stack, and we are going to name it as top element. And now we are going to check that whether that is the same value that is present for the map bracket value key. And if the values are not same, we can return false immediately as well. And if that is not the case, eventually if we get out of the loop, then we will have to check that whether the given stack is empty or not. If the stack is empty, we can return true, or else we can return false. Let's try to run this code. Okay, seems like our code is working as expected. Let's submit the code. And our solution is actually pretty fast compared to a lot of other solutions. So I would be posting this in the comments so you can check it out from there. Thank you. Hello friends, hope you are having a fantastic day today. So once again, we are going to do an awesome LeetCode problem that is extremely popular at all sorts of IT companies. So without any delay, let's get started. So the LeetCode problem we are going to solve today is called largest rectangle in a histogram. This is a LeetCode hard problem and also an extremely well-liked problem. Now the statement is quite simple and straightforward. We are given an array of integer called heights that represent the histogram's bar height, and we are also told that the width of every single bar is 1. Now we need to return the area of the largest rectangle that we can make inside this given histogram. So this is all we need to return. And now let's try to understand this with an example. So for this, we can make a rectangle that looks like this. Now the area of this rectangle is going to be 2 because the width of this portion is 1 and the height of this portion is 2. So 2 times 1 is going to be 2. So same way, there are multiple different options we can have in order to generate the area, but we need to find the maximum area. And in this case, the answer would be retrieved using these values, where if we make a rectangle like this, using these two bars. So now in this case, the area is actually going to be 10. Why? Because the height of this portion is 5, and for this one the width is 2. So 2 times 5 is going to be 10. So this is what we need to find, and this is what we need to return. So brute force approach is actually quite straightforward and very simple. Now one thing we can do is that we can take this one single rectangle starting at position 0, and then we can see that what are every single possible areas we can make. So one area would be like this, second area would be like this, the third area would be something like this, fourth area would be something like this, and so on and so forth. And eventually we do every single possible combination based on every single position of the given rectangle bar height, and then eventually we would find a solution like this that contains the most optimal approach, and this solution would work fine. We would be able to eventually find the answer, but this is going to work in big O of n square time, because at every single time we are doing a lot of extra and overhead work. So what is the most common thing we can imagine? Well, number one observation we can make is, because we can see that the height for this 0th index is 2 at the moment, but the moment we want to consider this first index as in combination with this 2, then the maximum height we can imagine is only going to be able to 1, which means we are only at the higher height until we encounter a height that is lower than our current height. And whenever that happens, we will have to start considering the lower height, and we need to understand a couple of things. If we want to calculate the area, we need two items. First item is the height. So we already know that which height are we going to consider based on the lower height compared to all the other possible heights. That is number one observation. Second observation is we need to consider the width. So width we can simply calculate based on the current index position where we have, or we can also keep track of that where did that height started existing. That in terms of finding the right side boundary of any particular rectangle, we can only find it until we find a lower height that reaches. So there are actually three examples we can see very easily. First example is at this position number 2, or this initial first position where the current height is 2 and the current height is located at position number 0. But the moment we try to consider the next element, we will have to get rid of this height too, because now it is no longer in the existence, which means the maximum area we are being able to generate using this bar 2 is only going to be 2. Okay. Now next thing, another example is we just saw with the value number 5, that with value number 5 we can only say that we can use rectangle 5 or bar 5 until we reach to this index position number 4, and then so which means maximum area that this bar 5 can make is going to be of width 2 and height 5, so total is going to be 10. Same way for this 6 comes into the existence at index number 3, but since the height at index number 4 is actually lesser than the index number 3, which means this 6 only remains in existence just for one single bar. So the maximum area we can make over here is only going to be of size 6. And this is the whole logic. This is the whole meat of the solution. Now, after understanding this, we can actually make a suboptimal solution using the same very simple approach, and then we will try to improve upon that solution. So the suboptimal solution that I'm proposing is that at every single position we identify that what its right side boundary is and what its left side boundary is. So what is the maximum height and width we can make, and based on that we can do all sorts of calculations and then find the solutions very quickly. So let's try to see this solution in action. The idea is at this position, the maximum left side height we can make is 2. The maximum right side height we can make is also the maximum width we are able to achieve is 1, which means the maximum area we can generate is only going to be 2. For this position number 1, the maximum width we are able to achieve is going to be 6, because this 1 remains in existence throughout this whole process. And the maximum height we can achieve is only going to be 1. So over here maximum area we can make is only going to be 6. Now at this 5, the maximum left side we can go is only up to 2 because it starts at position 2. The maximum in terms of right we can go is only up until position 4 or before position 4. So up to 2 and 3. So width is going to be 2. So over here we can make the area 10. For this height 6, we can only make the maximum height as 6. Same way at this position number 2, the maximum we can make is actually going to be this much, where currently the width is going to be 4 and the height is going to be 2. So maximum area we are able to generate is 8. And same way at this 3, the maximum we are able to generate is simply going to be just this one, because one before that is actually in the lesser height. So we can maximum area we can make using only or the entire height of this area is going to be 3, and in the end we can simply return 10 as the answer. So what we did is, for every single element we try to see that what is the left limit, what is the right limit, and what is the total area we are able to generate, and then we can very easily store the answer. Now this solution would just be good if you provide this solution in an interview. It might even work, but the thing is there exists a better solution where if we just use stack to keep track that what is the current index position and until what previous index positions we are maintaining that height, then we can very easily solve this problem. Why we need to use the stack? Because think about it, for every single position we are only going to have that position in existence until we find another bar with a lower height, which means the moment we find another bar with a lower height, we can actually go back to the elements that are already present inside the stack with the higher height and calculate the area. That's it. That is the whole logic. So now let's try to see the solution I'm proposing in action. So now let's just quickly initiate our stack. Now inside the stack, we know that this is going to operate in terms of last in first out principle. And the other thing is we can actually keep track of the bar heights, but then we would also have to find that what was the initial position of this particular value. So rather than, a better approach is that we actually store the index values, and using the index values we can quickly look up that what has been the bar height at that position in big O of one time, because we already know the index position, and then we would be able to also calculate the width depending on the current index position and the existing index position inside the stack. So let's try to see the solution in action. So initially stack is empty, okay, and we are also going to have a variable where we are going to store the area. So let's just mark this one as max area that we have been able to calculate so far. Okay, so initially stack is empty. Now we are at this index position number 0, so we add index position 0 inside our stack. Okay, and currently we know that this height is 2. Now next thing is we iterate over to the next element and we identify that currently we are at index position 1. So the height at index position is actually less than the height we currently have on the element that is already present inside the stack, which means this position of this element 2 is no longer relevant because we found out a value that is lesser inside the in its existence, which means this only exists until this portion. So we will try to we will pop this element out and we will calculate the possible area that this element has been able to generate. So currently for this first position, this has been the area it is able to generate. That area is going to be 2, that is the height, and multiplied by width, that is 1. So the maximum area we have so far is 2. Okay, now once again we are going to add value number 1 inside our stack, saying that currently 1, so the height of this 1 is also 1, and currently we will only pop 1 out when we either reach to the end of the array or end of the heights, or we find some place where the height is actually 0 and then we have some more elements. Okay, so this is always going to be relevant in this example. Now we are at index position number 2. So notice what happened at index position number 2. The height suddenly increased compared to what the height we already have, which means this 1 is still valid. So because it is still valid, we are going to keep it inside the stack, not popping it out, and we will add one more element 5 or this index position 2 on top of the stack, because now this is also relevant so far. So we are going to put 2 inside the stack, so its subsequent value is bar height 5. Then we identify height 6, which means this 5 is still relevant. So because 5 is relevant, we are once again going to add value number 6 on top of the stack, or sorry, not value number 6, but the index position of 6, which is value number 3. So we put value number 3 inside on top of the stack, and the height is 6. Now we suddenly encounter the value at index position number 4, that is height 2. So any single value that has greater than 2 height has to be popped out of the stack, because now that is no longer relevant, which means first of all this 6 is now no longer going to be relevant because the height is 6 and currently this index position is 3. And notice that the index position for this bar height 2 is 4, which means depending on the index position difference, we can actually calculate the width for which this 6 was relevant. So 6 was currently relevant for width 1. So currently let's pop 6 out. If we pop 6 out, currently this 3 is no longer present. We know that this was relevant for 1 width, which means width was 1 and the height was 6. So now the maximum rectangle we have been able to find is of size 6, which is greater than the previous maximum we had. So we are going to update that. Okay. Now are we done? No, because this is 2 and this value is 5, which means we would still have to pop one value out. If we pop one value out in this case, now notice that the height at this position is 2 and the height at this position is 4. So because this is a greater position compared to over here, so what is the width we found? The width is actually 2 and what is the height we have is 5. So this is the height, and also let's get rid of this 2 from our existing stack. Okay, and now this area is going to become 10. So let's just add an area 10. Now once again we have this element 1 and currently this element is 2. So 2 is greater than 1. So because 2 is greater than 1, we are not going to pop 1 out because this 1 is still relevant. So we are just going to simply add 2 on top of 1. So let's just quickly add this index position number 4 with the height 2. Okay, and now currently next one we found the increase inside the height, which means this 2 is still relevant. Because this 2 is relevant, we are simply going to add an element 5 on top. So we are going to add element 5 on top. Now adding index position number 5, now we reach to the end of the array, which means the moment we reach to the end of the array, we will have to start popping every single value out compared to its current position. So currently we pop value number 5 out, which means what is the height over here? The height is 3. What would be the width? Width would only be 1 because it is only relevant for this one portion, because currently we are at the end of our loop. So the area we have been able to calculate by popping this value number 3 out is going to be 3. Now currently 3 is less than value 10, which is the maximum area we have. So we are not going to update the maximum area. Okay, now we are going to next pop out element number 4. So if we pop element number 4 out, it has been relevant for this much portion of the time, which means currently we have 2 multiplied by 2. So the area is going to be 4. 4 is also less than 10, which means this area is also not relevant. And last one, we will have to pop element number 1 out that has the size 1 or the height 1. So for this, height is going to be 1, and this has been relevant since position 1 until the very last position. So this has been relevant for the width 5. Oh, sorry, for the width 6. Since the very first position it has been relevant. So now because this has been relevant since position 6, so the maximum area we have been able to generate is also going to be 6, but still it is not greater than the maximum area. So after the end of this loop, we can simply return the max area to be 10. And that's it. That's the whole answer. Now if we see time and space complexity, in this case the time complexity is going to be big O of n, and the space complexity is also going to be big O of n. So the coding solution is actually quite straightforward. First, we have a variable called max area where we are going to be storing the maximum area we have been able to identify so far. Then we have our stack that we initialize, and we also have a variable n to store the length of the given array. Then we have our for loop to iterate over the given array. Now first we check for a condition that if the given I is equal to n, which means we have already crossed every single element, then we can mark the current height as 0, because this is to take care of the last element. If that is not the case, we simply take the value of the given subsequent height from the heights array. Okay. Now we have our while loop where we check that while the given stack is not empty and the current height that we have been able to identify for any given ith element is less than the current height that is already present inside the very first element of the stack, then we will have to calculate the area for that, where we simply calculate the height based on by popping the element out of the stack, and then we calculate the width by subtracting the value of the current I minus the current element that was present inside the stack minus 1, and then we calculate the max area where we compare two elements based on the given max area that we have been able to identify so far, and the given current height and width multiplication, or the current area that we have been able to identify, whichever is greater, we are going to keep it that. And in the end, after we run out of this while loop, we are still going to push the current element inside our stack. And by the time we are done with all the elements, we should have our maximum area being populated with the correct value, and then we can simply return that. So now let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And once again, our solution runs beautifully, extremely fast in terms of time and space complexity. So once again, the solution is present in the GitHub repository. The link is in the description, so you can check it out from there. Thank you. Hello friends, hope you are having a fantastic day today. So once again, we are going to do an awesome LeetCode problem that is really popular amongst tech companies for the interviews. So without any delay, let's get started. So the LeetCode problem we are going to solve today is called longest valid parentheses. And you can see that this one is a LeetCode hard problem and also an extremely well-liked problem on LeetCode. The problem statement is actually quite simple, where we are told that we are given a string that contains just the characters opening circular bracket and closing circular bracket. And now we need to return the length of the longest valid parentheses substring. Suppose we are given a string like this. Now we can see that all of these are actually valid substrings because they are coming in correct order. So in this case, since all of them are correct, we can say that the longest substring that is valid is currently of 6 characters. Same way, let's try to take one more example. Suppose the string we are currently given is something like this. Then we only have a valid substring that is only valid for just 2 characters, and these two are not part of the valid substring. So okay, so we need to calculate that what is the consecutive longest valid substring, and we need to return that. Now, brute force approach, logically, we are going to do the most simplest things possible, where we are simply going to check that for every single substring starting from any particular string, we are going to check that what are the longest substring we are able to generate until we encounter some invalid substring. So overall, this approach is a very simplistic approach that would work fine and generate the result. But the issue is this would operate in big O of n square time. So we need to find some way to shorten this calculation, and in a single go we need to identify that what are the current substring that we have been able to find, is it valid or not, and if it is valid, what is the current length, what is the maximum length we have been able to identify, and subsequently at what point does it stop becoming valid. So these are the questions we will have to answer, and then only we can find the optimal solution. So now let's start looking about that what an optimal solution should look like. Suppose this is the string given to us as an input, and now we are trying to find the solution. Now let's try to make some understanding clear, and that would help us build our solution. Number one thing is, the moment we identify at any given moment that there is a closing circular bracket and we haven't found the opening circular bracket, which means we can directly ignore this case because this is definitely invalid because it does not have any previous opening curly bracket. That is number one observation. Number two observation is, for any single opening curly bracket, we will need to keep this information stored somewhere, that we have one open bracket for which we are trying to find a subsequent close bracket. So it can come over here, or maybe it cannot be possible, but we will need to have that information. So these are the two pieces of information we will have to consider. Third thing is, it could be possible that we may find some existing valid sequence like this, but this may not be the longest valid sequence, because longest valid sequence in this case is probably going to be this one. So which means we will have to keep track of the current sequence, and we will also have to keep track of the valid sequence and also the longest sequence. Considering all of these things, it would make really good sense to use stack data structure for this problem. And why are we using stack? Because if we have to consider this to be valid, then immediately before this there has to be an open bracket, then only we can say that this is a valid scenario, and then this bracket would not be considered, which means this still needs to live inside the stack, because stack follows an awesome property of last in first out that is going to be greatly helpful to us. So now using stack, we would be able to solve many different problems. And the idea is that for each of this position, rather than just storing whether it's an open or curly bracket, we can actually store the index values. So let me write down the index values. And now the thing is, inside the stack, we will only push values when we encounter some open bracket, because it could be possible that sometime in the future there might be a closing bracket. So, and whenever we identify a closing bracket, we will try to see in the stack that whether there exists any particular bracket that we can pop out. If it does, then it would be part of the valid sequence. If it is not there, then we will see all sorts of scenarios. Okay, so I hope that all of these explanation makes sense, and now you are able to understand that how we are actually going to use the stack for our solution. So let's quickly generate the stack. Now we are going to keep track of a few variables. So first one is that what is the current length we have been able to find. Next, what is the maximum length we have been able to achieve. Now in order to keep track of the current length, we will need to know that where does the current valid substring starts. So initially, because we are actually using this as 0, so initially our starter pointer needs to be somewhere over here before 0, because we are starting the index from 0. Because imagine a scenario where we are only given an input like this, which means this is 0 1. So based on the index location, we know that this is actually a valid substring of size 2, but because we are starting the index from 0, so we will actually create our initial starting pointer from -1. So it would be very convenient for us to calculate these values. Okay, and you will understand the logic once we iterate over the example. So initially, our starting pointer is going to be located at -1 position, and this is where our starting pointer is. Okay, so now let's quickly start iterating over the solution. So logically, first here we identify that this is a closing bracket. For closing bracket, we will have to pop one element out from the stack. But the thing is, currently stack is empty. So because stack is empty, this has to be an invalid entry. So we can ignore this case and move on to the next element. But when we move on to the next element, we can say for sure that this is never going to be part of the valid substring. So we will need to update our start pointer. So now we will have our start variable being located at position number 1. So let's just mark our start variable at position number 1. Current length is 0 and maximum length is also 0. We haven't been able to find any values. Okay, so let's just mark these. Now we encounter an opening bracket. So the moment we encounter the opening bracket, we are going to be pushing the values inside the stack. So let's mark the index value. Same way, once again we identify an opening bracket. So once again we are going to mark a value inside the bracket. And when we are opening the brackets, we don't need to update the current length or the maximum length, because we haven't find any valid substring so far. Okay, now we identified one closing bracket. So the moment we identify a closing bracket, we will have to pop element out of the stack. So let's try to pop one element out of the stack. If we pop this element out of the stack, by the way, this has to be number 2. Okay, by the way, so number 2 index we are popping out of the stack, which means that currently what has been the current length we have been able to identify it so far. That is, so currently we are at element number 3. The element we popped out is located at element number 2, which means now this is no longer present over here, which means currently we still have one element that is left inside the given stack. So far we can do the difference between this current element and the element that is already present inside the stack using the peek function. So the difference is 3 minus 1. So far we have been able to identify a length of 2 size valid string. So let's update the value that the current valid string that we have been able to find is of size 2, and the maximum length we have been able to identify so far is also of size 2. Now notice that we are not using the start variable right here because this is still not taken care inside the existing valid substring. So that's why as long as there are some values present inside the stack, we cannot conclude that stack is empty and we have taken care of every single substring. So that's why start pointer is still going to remain here. So now let's move on to the next element. Now we are at position number 4. Once again, we identified the opening bracket. So let's try to add one more value inside our existing stack. So now the value is 4. Okay. Now once again we identified a closing bracket. So the moment we identify a closing bracket, we will have to pop one element out. So let's quickly pop this element out. Now the element that is currently left inside the string is of size 1. So because this is of size 1 and the current element we are at is of size 5, which means the current substring that we have been able to find is 5 minus 1. So this is going to be 4. So current length that we have been able to find, the current maximum length is of size 4. And because this is of size 4, which means we will also have to update our maximum length as well. And that is also going to be of size 4. Okay. Now currently inside our stack, we only have one element that has been here for quite some time. And now let us also try to move to the next element. So once again, we identified one more opening bracket. So we will try to put element number 6 inside the bracket. Now once again, we identified the opening bracket. So we will try to put element number 7 inside the bracket. And now at element number 8, we identified, and by the way, this current length would be reset every single time we update the value. Okay. So this is always going to be reset because we don't know that what the current length is. We only define the current length based on the value we pop out. So now this is a closing bracket, which means we will have to pop one element out. So now we are located at value number 8. We popped element number 7 out, which means we still have one more open bracket located at element number 6 that we haven't taken care of. So now we will do the difference between 8 minus 6 and the value is 2. So current valid length that we have been able to identify is of size 2, but that is not greater than the maximum length we have been able to achieve. So we are still going to mark this as value number 4. So this is the logic on how you can actually use stack to solve the problem. Now let me just show you one more example very quickly and then we will move to the coding solution. Basically this is the optimal solution. So now let's just quickly start using the logic. So currently we identify an opening bracket. So we are going to mark value inside the stack. We once again identify a closing bracket. So once again we are going to pop this element out of the stack. The moment we pop this element out of the stack, and currently the stack is empty. If the stack is empty, then we found a valid string from the starting value. So we are going to do the subtraction between the current value minus the starting value, which means 1 minus minus 1. So the answer is going to be 2. So the current length that we have been able to identify is 2, and the maximum length we also identified is also 2. Okay. Now once again, so far remember this s is the starting value is still going to remain here, but now we identified a closing bracket, but for this closing bracket we don't have any value inside our stack. So because this stack is empty, which means this is an invalid portion, so now the starting value has to jump. So now we are going to jump our starting value to start at this element number 3. Okay. Now at this element number 3, we identify an open bracket. So we are going to add value number 3 over here. Once again for 4, we identified a closing bracket. So we will pop an element out of this loop. So currently the stack is empty. If the stack is empty, so now we are located at this position number 4. And by the way, our starting position should be at this position number 2. Okay. So now currently we need to, because stack is empty, we will need to do the difference. So the difference between current index and starting index is going to be 4 minus 2, so value is 2. So this is the current length we have been able to identify, and this is for this portion. So now maximum length does not need to change. Once again we identify an open bracket, so we are going to add value number 5 over here, and once again we identified a closing bracket. So now we will have to pop this element number 5 from the loop as well. So currently the string is empty. Because the string is empty, we will have to do the current value minus x. So it's going to be 6 minus 2. So once again, the current length we have been able to identify is 4. So the current length needs to be updated. This is going to be 4, and because this is greater than our maximum length, so we are also going to update this one. And because we reach to the end of this our given string, so we can return the maximum length as 4. So this is the whole logic that we can use to solve this problem. And by the way, if we see time complexity in this case, the time complexity is going to be simply big O of n, because we are simply iterating the given input array just once. If we see space complexity, because we are using an extra stack, it will also going to be big O of n. So the coding solution is actually quite simple. First, we have a variable to store the maximum length. Then we initialize our stack, and then we initialize the first value inside the stack as -1. This is going to be our starting pointer. Okay. Then we have our for loop to iterate over the given string s. Character by character, we check that whether the given string, if that is an opening bracket or a closing bracket. If it is an opening bracket, we simply push that index position into the stack. If that is not the case, then there can be a couple of scenarios. So in either scenario, first we will have to pop the element out of the stack. Now after popping element out of the stack, if the given stack is empty, then we need to push the current index as the base for the next valid substring. And if that is not the case, then we are going to calculate the maximum length. So for maximum length, we are simply going to do the to compare the current maximum length minus I minus the peak that is currently present inside the stack. And this is going to be give us the current length that we are dealing with. And in the end, we simply need to return whatever the max length we have been able to identify. So let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs extremely fast, and this is a very good time and space complexity. So once again, I would be posting this solution in our GitHub repository, so you can check it out from there. The link is in the description. Thank you. Hello friends, hope you are having a fantastic day today. So now we are going to do an awesome stack problem that is actually a LeetCode premium problem. So this is going to be really interesting, very popular question and very interesting subject. So without any delay, let's get started. Okay, so the LeetCode problem we are going to solve is called max stack. This is actually a LeetCode hard problem, and the thing is, because this is a LeetCode premium problem, I took this description from another website called leetcode.ca. So thank you so much to whoever maintaining that website. Now we need to design a max stack class that supports these 5 functionalities. Now, if we see the functionality, the first 3 are pretty common, where we are pushing an element down the stack, where we are popping an element out of the stack, and where we are just checking what is the top value inside the given stack. These 3 are the common functionality of any particular stack. Then we need to add 2 more methods, where first one is a peak max method. And second one is the pop max method. So if we do the peak max method, we will need to know that what is the maximum element currently. And if we do pop max, then we will have to pop the maximum element that is right now inside the stack outside. So let's try to see the solution for this problem. So logically, let's assume that currently we have an empty stack. Okay, so we have the option to use 5 operations, and so let's try to first quickly push some elements inside down the stack. So if let's push value number 3 and then value number 5 and then value number 1. Okay, so now currently we pushed a few elements. Now if we want to pop, and let's just add one more. Now if we want to pop, we can pop one element out as well. So if we do the pop operation, then we won't have value number 7. Now we can also do a peak operation. So if we do peak operation, then we can simply check that what is the very first element. So answer of this is going to be 1. Then if we want to do peak max, which means we should see that what is the current maximum element present inside the given array, which means the current maximum element present inside the given array is actually value number 5. Even though it is not at the top of the stack, this is the current maximum element. So this needs to be value number 5. And if we have to pop max, then we need to pop the value number 5 out of the stack, not value number 1, even though 1 is the very first element. So this is how we will have to design this algorithm and design data structure in order to keep these values. Now we know that completing these items is very simple and very similar. No issues with this one. This is a regular stack functionality, and every single language like Java, Python, C++, they all have their own stack versions that we can simply use. The problem comes when we need to do this peak max and pop max operations, because the thing is, this is actually slightly complicated because of variety of reasons. Now the very first thing that comes to our mind is to have a variable called max, where we are going to store the maximum value that we have been able to identify inside the given array, and this should make our lives easier. This is the primitive logic we can think of, where let's assume that we add value number 1. So we need to update the value of max to value number 1. Then once again we add value number 6. So we once again, because 6 is greater than 1, so far the maximum element we have been able to identify is 6. Then we have value number 3. So 3 is not greater than the current maximum element, which means we don't update anything or we don't do anything. Now after this, let's say we add a value number 8. So once again the maximum element needs to be 8. So far you must be thinking that, hey, this seems pretty convenient. Why don't we just have one value to keep track of the maximum element, and at any given moment I want to see that, hey, what is the maximum element? I can just simply look at this variable and find the answer. The problem is, when we do the pop operation out of this given stack, then there would be an issue, because now let's say that I decide to pop this 8. So if I pop this element 8, I know that now 8 is no longer the maximum element present inside the stack, but I don't know what is the other element that is the maximum element. But instead of just having one simple variable max, we actually need to have a variable, another stack called max, where for every single entry inside the original stack, for that entry we will have to keep track that what has been the maximum element that we have been able to identify it so far, and keep updating that list depending on the how we push out or pop out the elements from the given stack. So let me try to explain what I mean. The idea is, let's assume that for the max we have to worry about two operations. First one is the peak max, where we are simply watching that what is the max element that is currently present, and second one is the pop max, where we are popping the maximum element out at the current position inside the given array. So we have created our own max stack array. Max stack. So this is our max stack and this is our regular stack. Okay, now let's assume that I wanted to enter value number 1. So what I'm going to do is, I'm going to add value number 1. Currently this max stack is also empty. So far the maximum element at this position I have been able to find is also 1. So I'm going to store value number 1 over here. Once again I identified value number 6. So because value number 6 is greater than 1, I'm just going to put 6 as normal value over here. But over here, because say value number 6 is greater than value number 1, so I'm going to say that up until this point of the stack, the maximum value I have been able to identify is 6 that I have presented over here. And some reason, if I decide to pop this element out of the stack, then I know for sure that this element also needs to be popped out, and then the maximum element at this position will be corresponding to the maximum element at this position, that is value number 1. So which is pretty convenient for us. Now let's try to add one more element, let's say 3. Now once again, even though we added value number 3 over here, so far the maximum value we have been able to identify up until this point is once again 6. So we are once again going to mark value number 6 over here. And then once again, let's say we add value number 8. So once again, we are going to add value number 8 over here, because that is the maximum value we have been able to identify. So far, let's repeat what we have done. We did the push operation in big O of one time, no issues with that. Now at any given moment, we can also do the peak operation And the moment we do peek operation, whatever element is located at the top of the stack, we should be able to see that. So this is also going to happen in big of one time. So once again, no issues with this one. So we already took care of two variables. We can also do the pop operation easily from the stack. So pop operation can also be done in big of one time, and we can do peek max as well in big of one time, because this is also being happening or maintaining in constant time. So this also happens in constant time. So we took care of 4 operations in big of one time just by simply using these two different stacks. But now the important thing is that how we are going to manage the pop max operation. For that, we will also have to do the pop. So let's try to first do a couple of pop operations. If I pop element number 8 out of the given stack, which means now stack does not contain 8 value anymore, and I will also have to update the maximum element up until this point as well. Okay, now at this position, let's say I decide to do pop max. So if I do pop max at this moment, I should not be kicking out value number 3 from the stack, because this is not the maximum element so far. The value I should be kicking out is actually going to be the value number 6. So what I'm going to do is that I'm going to kick value number 6 out of this given list up until every single point that I have been able to iterate so far. And the moment I kick value number 6 out, I'm going to do a peek operation to see that if this given current maximum value, if that is greater than the current maximum value I'm left with. And if that is the case, then I will need to update the given max element to incorporate value number 3 as well. Because remember that in the previous state, in this state, we did not had value number 6 as part of the given value number 3 as part of the maximum value so far. But because we did the pop max, we kicked a value number 6 out, and at the same time we will also have to pop these two elements out as well, and we would be left with value number 3. Okay, so this is the whole thing that we need to do, and this is how we can solve this problem using two stacks in order to convey this message. So this is the whole solution, and using this we can complete everything in big O of one time, all 5 operations. So now let's quickly see the coding solution, and then things will make much more sense. Okay. So now, since this is a LeetCode premium problem and we don't have that subscription at the moment, I'm just going to explain you the solution in the notepad, but this code would work fine, and the code is also present in our GitHub repository. So let's understand the code. So first we are going to create couple of stacks for stack and max stack. Now for the push and for the pop and for the top, we need to, all of these 3 are standard operation. The thing is, pop and top are going to remain the same. The only problem is that for the push operation, we actually have to push the element in both the places, which means in the stack, we are just going to push it as a regular push entry. But for the max stack, we will first have to check that what has been the maximum element inside the given stack based on the definition of this X value so far, using math.max function and checking that what has been the current maximum in the max stack versus the current value we are trying to enter. So we are always maintaining the maximum element for any given X element inside our max stack. Okay. Then for the pop operation, we will have to pop the element from both the places, max stack and also from the given regular stack. For the top operation, we simply have to check that what is the maximum element on our regular stack, and we can just do a peek operation. Now for the peek max operation, we will need to do the same operation, but now this time in our max stack rather than our regular stack. And the last one is the slightly more complicated method, that is the pop max method, where first of all we are going to initialize a new stack called buffer, because remember the value we are trying to kick out is presented somewhere in the middle in the regular stack. So meanwhile we don't find that value, we will have to buffer that from our regular stack. So that's why we are going to push every single element from our normal stack to the buffer stack until we find the top element to reach to the max, and then we will simply pop that element out from the regular stack. At the same time, we are also going to pop that element out from our max stack as well. and then in the end, inside the buffer, we are also going to push all of those elements into our regular stack using the elements that we just stored inside our buffer stack temporarily. So that's why this pop max method is slightly complicated method, and you can see the coding solution present on our GitHub repository. So hopefully this explanation made sense to you, and yeah, thank you so much.